electrowetting is, why is it important, and what has been done before in this respect. Then we will talk a little bit about physics, basically how and why we obtain the equations that we will be interested in. After that, we will go into the analysis of the model, so basically existence of the solutions to this problem. Concerning numerical discretization, I will focus mostly on one of the subproblems that arise in this system of equations that you will see in a little bit. Basically, Canhillier Navier-Stokes with some funny boundary conditions that you will see. I will show you a couple of numerical illustrations, and I will conclude. Okay, so this picture is basically the standard prototype of how electrowetting works, of what electrowetting is. So in principle, you have two conducting plates, and in between them you have sandwiched a droplet of a non-conducting material. Think, say, for instance, water, and it's surrounded by air. You basically apply a voltage pattern to one of the plates, and the electric actuation makes the surface tension between the two fluids change. And well, as the picture shows, then you get movement of you get the droplet to form, or even eventually to move to splits, to merge with other droplets, and so on. So the official definition of electrowetting would be the property that by electric actuation you can change the surface tension between two fluids. Obviously, this allows you to manipulate these flows, and this has a lot of applications. Say, for instance, on lab-on-chip systems, the autofocus lenses that cell phone cameras or digital cameras in general have are based on an electrowetting device. The new generation Kindles, the e-readers that are that have color, they are based on electrowetting because that allows you to, say, for instance, read in the sun without having to worry about the reflection. Coincidentally, last week I stumbled upon a paper in Nature where well, the authors proposed to insert a device in your shoe, and well, there was a liquid there that every time you step, you press it, and that will generate a voltage. And using that voltage, you can, say, for instance, charge your phone while you walk. So, pretty neat application. So, I think I convinced you that this is something very important, and that should be treated. We should have a model and computational techniques for this phenomenon.
Excuse me. What's
Yes.
the difference between the first and the third model?
No. This is the process.
Oh,
so
it's like
it was here. Yes, it was here. We apply a voltage. It moves.
And then the distance between two plates is very small. So
That was my next sentence.
Average thickness and probably have just a plate. Something.
Let me go to the next slide. Let me go to the next slide, because that's exactly what I wanted to say. We are not the first ones to look at this, and first approximation is exactly as you said. The distance between the two plates is small, so we average or basically ignore them. And so, for instance, in 2007, Andrea Bertozzi and her collaborators proposed a Canhillier model for this phenomenon. Again, you average, so you're basically looking at the droplet from above. John, back in the days when he was a PhD student, he worked on this too, and he proposed also a model that's instead of having a diffuse interface or a Canhillier model here, he had a sharp interface. But most importantly, one of the great things about this work, I think, among many others, is that he was able to introduce the phenomenon of contact line pinning, which is, well, I will talk a little bit with more detail about it later. But in 2 words, this is just some type of frictional effect, and having that is very important to capture the true scales in which, say, the droplet is moving. Concerning 3D models, as far as I know, the only works that have been done are by Gunter Grun and his collaborators in a couple of papers where they basically study existence of solutions to the system that arises. They, however, consider only a droplet that density as the surrounding medium. So the only material property that appears is, say, surface tension. And they say that the droplet is not moving. In this paper, they propose a model in which they have a charge distribution. So what I'm going to talk about today is going to be pretty similar to this paper, although much more general. And in this, they consider also ion concentrations. And so the charge is given by the difference of the ion concentrations. So what we want to do is to have a fully 3D model. Although, yeah, it would be pretty reasonable to average. We want to do it in 3D. We want to have the model derived from physical principles, not just experimental observations. And we want to incorporate the principal effects. So, for instance, the difference of material properties between the two fluids. I was saying that, say, the droplet is water, the surrounding medium is air. The ratio of densities is about 1,000. So there's a lot of there's a big difference there, and so the inertia of the droplet should be taken into account to have a very realistic model. We want to, of course, incorporate electrostatic and, if possible, contact line pinning. So let's talk about the derivation of the model. So as the title of my talk said, we are going to talk about diffuse interface model. And well, in diffuse interface methods, what you usually do is that you introduce a phase field variable. Say it's going to be -1 in the air, it's going to be +1 in the water, and it's going to have a smooth but tiny interfacial layer in between them. This is basically done so that you do not have to track the interface. Topological changes are handled more easily, and well, say all the quantities that are related to the geometry of the interface or curvature. So, for instance, surface tension are handled more easily. So, of course, this phase field is going to be moved with the flow. So, its evolution is going to be described by a transport equation, maybe with some diffusing flux. We say that the fluid is going to be Newtonian, incompressible. So, of course, its movement is going to be governed by the variable density incompressible Navier-Stokes equations. Of course, we do not know what boundary conditions this problem should have, or what are the forces that are exerted on the fluid. And basically, that's what we're trying to find. We said that we are going to apply a voltage to the plates. The voltage is going to generate an electric field. The electric field is going to generate a charge distribution. And of course, these have to be governed by the Maxwell's equations. Here we make the first simplification. And this is that the velocity at which the droplet is going to move is going to be very small compared to the speed of light, which is obviously something very reasonable to assume. And so in the, I think it's Faraday's law, we drop the magnetic effects. Well, D is the electric displacement field that is generated by difference of potentials, where epsilon is the permittivity of the medium, which of course can depend. It's going to depend on the phase, it's going to depend basically on V. So we write the energy of the system, which is basically a positive. Well, I didn't write the exact expression because it would take a whole slide and it wouldn't give you much information. But basically, it's a positive definite functional on the state variables, so on the phase field, velocity, the displacement field, and the charges. And we recall the first law of thermodynamics that tells you that the energy in a system is equal to the work minus temperature times the entropy. I'm sorry. Then, well, we take its time derivative, so the change of energy. And we do so because when we do that, there are some terms in the energy that are going to be something times the velocity. So that is clearly going to correspond to the power being generated. Now we say this is a closed system, so the network is going to be 0. And so this term, I don't know, do you have a pointer? So I don't have to be.
That should be a pointer right there on the
said that the system is closed, so the network is 0. And so from this expression, this being 0, we can find what are the forces that are going to be acting on the fluid. Of course, these are going to be expressions that are going to depend on the state variables and maybe the diffusive fluxes that we introduce. To close the system, we need to find expressions for the fluxes, and to do that, we need to introduce dissipation functional. So we need to basically describe how the system is losing energy or transferring one type of energy to the other. The only thing that physics tells us is that the dissipation function needs to be a positive definite function. Obviously, the simplest expression of something like that would be something quadratic in the fluxes, which is the expression that we take. Moreover, we take it to be diagonal in the fluxes. It's a simplification, but it seems very reasonable, at least at this stage. And
this comes from experimental. I mean, this experimental. Because any model has some experiments. This one is not mathematical.
No, as I'm saying, well, the only thing that we know is that it should be positive. So let's take it quadratic and diagonal. But yes. Yeah. So the next step, it would be to obtain constitutive relationships for the fluxes in terms of the state variables, and that's using non-Sagar principles, which is basically just formalization of, say, stress-strain relations or such. Going over all these steps, lengthy formulas, and so on, we finally, as I said, this is an assumption. This is a modeling assumption. And well, although physicists say that Sagar's principle is the ultimate truth, once you ask any physicist what is behind this, what are the reasons why this principle is true, they cannot give any definite answer. So I would say that this is a modeling assumption as well. If you don't want to think in this way, we are just saying basically that the fluxes are linear with respect to the state variables. Okay, after all these steps, we finally obtain the equations that are going to govern our model, plus the boundary conditions. So the phase field, as it is usual in phase field models, is going to be governed by a Canhillier equation, where phi is the phase field variable, mu is the chemical potential, so basically the derivative of the energy with respect to the to the phase field. W is the Innsbruck-Landau potential. It's the one that is going to prevent your phase field from going away from its natural state, so -1 and +1. The chemical potential is going to depend as well on the voltage and the velocity. Then, well, here are the definitions of all the quantities. The boundary condition on the chemical potential is just impermeability, so the fluid cannot go into the solid walls. However, this boundary condition is very non-standard. First of all, it's dynamic, and what it's basically describing is the evolution of the phase field on the surface. So the evolution should be also some type of transport equation, which is basically what we have on the left, and the quantity is not conserved. That's why it's not, think about it, it wouldn't be something like a projection of a Canhillier equation to the surface. And it's not conserved because, as a very simple example, you had a droplet, that is what it was sticking to a surface, and then it, say for instance, because of gravity or something else, the droplet falls. The quantity that the phi that was here at the beginning is not the same that after a while when the droplet left.
Excuse me.
Yes.
Looking at the equations, the third line. So then is the normal direction. How is the tangential direction?
Where?
The third line.
Third line here. So yes, this is the tangential direction.
So the first part of the third line.
This the first one. This one.
That means that you have normal, some continuity in the normal direction, right?
Of the chemical potential, yes, which is basically telling you that the fluid doesn't go into the solid, or outside of the dictated by the energy on the wall, and the energy is given basically by the difference in surface tensions in the two phases, the surface tension between, say, the water and the solid, and the fluid and the solid.
So, what have you to enforce this kind of conditions in your numerical scales?
I'm sorry.
So, will you enforce this kind of conditions in your numerical methods?
Yes, I do enforce them. I mean, it's in some sense it is variational because, well, this is a normal derivative, normal flux, and this is something that involves a normal derivative. So it's non-homogeneous Neumann if you want. Okay, the fluid equations, nothing surprising. It's going to be governed by the Navier-Stokes equations. In this term, it's the usual term that appears when you have a phase field cantilever Navier-Stokes. And here, it is hidden the term that is going to express the surface tension between the two fluids. If we go back, sorry. Yes, we go back in the definition of mu. We have gamma, which is the surface tension times well, this expression. That is what is going to give you the surface tension. Plus some extra terms that physicists call the Maxwell stress tensor. Then we have, well, some extra terms that are going to be some forces that are going to be created because of the difference of potential or the difference of the charge distribution. The fluid is incompressible, as we assumed in the beginning. We have impermeability, so very logical. But the equation of the tangential component of the velocity is also something that is non-standard. Say, if the right-hand side was 0, that is what is known as the Navier boundary condition. So this, big surprise, is called the generalized Navier boundary condition, and it is basically telling you that there is partial slip of the fluid, and this partial slip is given also not just by the stress of the fluid, but also by some extra stress that is caused, again, by the difference of surface tensions. Of course, you have this tangential derivative of the phase field, which physically, or say in intuition, it should be active only at the interface. So saying the limit, if you're being very formal, this would be a Dirac distribution. So you have just an extra force at the point where the three phases meet. Then the charge distribution, well, is just a convection diffusion equation. And for the electric field, well, we are going to look not at the electric field, but the electric potential. And, well, it's a Poisson equation. However, this one is given in a larger domain that is going to take into account the fluid and the plates. And this is very important because at the plates there's some extra energy storage, which is actually what is going to do the trick, which is going to allow us to actually manipulate the flow. Okay, so as I said, something very important to take into account is the phenomenon called contact line pinning, which is basically a frictional effect. A simple way to understand what that is and to visualize it is, say for instance, you take a drop of some liquid and put it on a plate. You incline the plate slowly, it's not going to start roll immediately. There's going to be an angle for which it's not going to move. If you tilt it enough, it's going to start rolling. This is obviously some type of friction that is going to depend on the stress, and that is what is called pinning. There's not much consensus, or any, I would say, consensus in the literature about what is creating the pinning and how it should be expressed. So let's go in a phenomenological way. Anyways, we are going to do this only for the experiment, the computations, not for the analysis of the model. And the way we propose to do it is by recalling the generalized Navier boundary condition. Let's forget about the right-hand side for a second, and let's think about what this is telling us. Let's say, for instance, that the coefficient beta, which is called the slip coefficient, is very big. Then, to compensate, the tangential component of the velocity should be very small. And that means that, say, as beta goes to 0, you recover full sleep conditions. The other extreme is if beta is very small, this quantity is very small, and so you have that the stress is will equal to 0, so basically free sleep. So we propose to do something in the middle, and so basically we try to switch between these two regimes, depending on how big the stress is going to be. So we want it to be active only on the interface, so we say it's going to be something very big, 1 over delta, where delta is our transition length. That's for us basically infinity. If we are away from the interface, and this makes sense as well because, well, if you're dealing with a homogeneous flow, the correct boundary condition to apply would be no slip. If you are near the interface, then if the stress is not big enough, then we take something big, again, so that you recover no slip. And if the stress is big enough, then you take something very small so as to recover full slip. Again, this is completely phenomenological, and we use it only for the computations, not for the analysis.
But this boundary condition, right?
Yes, yes, yes.
Normally, all boundary conditions can be derived from the governing equations. When you take a limit from left or from the right and stuff. Is it possible to look at your, lots of your equations and extract something similar to this one?
Well, this one is obtained from the procedure that you mentioned.
Oh, I mean from the, it's not just, you invented it because it's convenient. It's
No. The generalized naive boundary conditions comes from all this variational process that we did. However, this expression for the slip coefficient is the one that I'm saying we cook up. Because in any case, nobody knows what is really happening at what is really causing this frictional effect. And so, if nobody knows, would you just propose something that works? And again, as I said, this is just for the simulations, not for the analysis. In the analysis, we're just going to take a slip coefficient that may depend, if on anything, on the phase. Then, as you recall, now we do a simplification. As you recall, we had some tangential derivatives on the boundary conditions. Say here, there was one. This is something that is very weird. It's very difficult to treat, or at least we do not know how. So we again go back to the intuition. What is really this term trying to tell us? This term is trying to tell us that whatever is being multiplied by the tangential derivative should be active only at the interface. And so what we do, and again in the limits, if we are going to do in some sense do the sharp interface limits, this should converge. It converges to anything to a Dirac distribution. So we replace this by exactly this Dirac smoothed out Dirac distribution. And here is the opposite. We do this for the analysis, but not for the simulations, because, well, in finite dimensions, this is something very well defined. Okay, after all these simplifications, all this discussion, we have that basically because of the way we obtained the system, which was basically from thermodynamically consistent expressions, we get an energy law. I don't pretend you to even read what is being said in this bunch of formulas. The important thing here is that, well, all the quantities that should be controlled are controlled, and also that this is obtained basically with variational techniques. So you take the equations that govern the flow, the motion of a quantity, multiply it by a suitable test function, integrate by parts 20 times, and obtain this. So this is, if you want, a formal energy estimate for this system. So some a priori bounds on the solution if it exists, and it's telling you as well which are the function spaces that you should take for the analysis of this problem. Okay, so based on this energy law is that we're going to construct basically our discretization. We're going to try to construct something that is going to mimic this property. We're going to construct it so that this expression makes sense, and so on. And this is what we're going to discuss in the analysis of the model. So, as you saw, the system was very complicated. There were a lot of expressions that it was not very clear how to treat. So let's fully discretize the problem. The problem was time dependent, so we introduce a time step. As usual, we chop the time interval into subintervals of equal size. And then to discretize in space, we use Gagliarkin techniques. So we introduce this spaces W that is contained in say H10 plus B of the larger domain. Q, X, and M are finite dimensional subspaces of these spaces. And as I think you guessed, the space W, we're going to use it to approximate the voltage. This guy, we're going to use it to approximate the charge, the phase field, and chemical potential. You don't have to use the same space for these three quantities. You could use one for the charge and a different one for the phase field and chemical potential, but let's keep it simple. And, well, this for the velocity, this for the pressure. And then we have a couple of compatibility conditions for these spaces. The first one is that if you take any function here, and you restrict it to the fluid domain, then you have this function has to lie here. And the second one, well, if you are going to approximate velocity pressure, then these pairs better satisfy the LBB condition, so they should be substable. Obviously, there's nothing extremely exotic about how to construct these spaces. If you construct, say, the mesh so that in a reasonable way, this is trivial, and there are several examples of how to construct this. So we know that such spaces exist. We know that they have nice approximation properties, and they satisfy the conditions that we want. Okay, so the fully discrete problem is, well, at each time step, we try to find a discrete voltage, a discrete charge, a discrete phase field, and so on. And they are going to, well, solve discrete versions of the original problems, the original equations that we had. So for the voltage, it's, well, just a discrete formulation of the Poisson problem that we had. For the charge, just a discrete formulation of the convection diffusion that we had, where the time is discretized using backward Euler. For the phase field and chemical potential, again, it's just a discretization of the Canhillier problem, where, however, we take the terms that involve the Ginzburg-Landau potential and the interface energy density explicit, and we add some stabilization constants that we take large enough. How large, we'll tell you in a second. This is in trying to make the scheme as close as, or the problem as close to being computable as possible. And moreover, having these things will allow us to say a little more about the quantities. Also, this type of splitting is not something that we came up with. It's very closely related to, say, for instance, the decomposition into the difference of two convex functions of Lowen group and Eliot that they do for Canhillier. Where, well, we just took very specific choices of these two convex functions. Well, then finally the velocity and pressure. As usual, we just have a discrete version of the Navier-Stokes equations. Okay, and well, we're not doing any type of splitting. We're just solving. If we are solving this, we are solving a saddle point problem. Of course, this is actually not a scheme; it's a problem, and this is not something that you can look at it and program it. First of all, because, say, for instance, here, for the phase field equations, you're taking information from the future. At this point, you do not know the velocity, but you are taking it as data in this equation, and the same for the previous equations. So this is not something that you can implement. This is not something that you can program. However, the nice thing about it is that because of the way we wrote it, because everything is fully implicit, this problem has a discrete energy law. This energy law is going to be a complete analog of the formal energy estimate that we obtained for the continuous problem. So again, we're obtaining a priori bounds on a solution of this problem if it exists. And moreover, these bounds are in the right spaces and independent of all the discretization parameters. So now that we know that if there is a solution, it has nice bounds, we can apply, after a lot of calculations, Leray-Schauder or Schaeffer's theorem, as I also heard that it's called, and conclude that for all values of the discretization parameters, this fully discrete problem is going to have a solution, and the solution is going to satisfy the same energy law. So we have existence for this fully discrete problem. Of course, we do not know yet how to compute these solutions. So we would like, and that's what this question is about, we would like to have an efficient and implementable scheme that converges to the solution of this fully discrete problem. It's a nonlinear problem, so the first thing to think about would be some type of Newton or fixed point iteration. Later, I will try to give a partial answer to this, at least for a piece of this full problem. Now, for every h and delta t, we have a solution. The solution is bounded in the correct norms. So we try to pass to the limits when the space discretization parameter goes to 0. And it is possible to do so, and so that's the content of this result. We can say that if the permittivity does not depend on the phase, then the semi-discrete problem, that is continuous in space and discrete in time, it's always going to have a solution, and the solution is going to have also some energy law or some bounds. This assumption, of course, is not very realistic. The material properties, say for instance, the permittivity, electric permittivity between the air and the water are very different. So this is not very realistic. But this comes from this term, which I will rewind. It is here. We are not quite sure, although, well, I think from our conversations these days, I think we know how to handle that, but I don't want to make any false statements. So basically, in the limit, we do not know how to interpret this term because, well, voltage is going to be, say, an h1 function. This is an L infinity function. So this is an L1 function. This test function should be in h1, so we're not quite sure how to make sense out of this in the limits. Okay, but as I said, at least in this somewhat restricted case, we know that there's always going to be a solution. Of course, the next step would be to pass to the limits in the time discretization parameter, which is something that we do not know how to do yet. And the main difficulty is basically that, if you recall, we had time derivatives on the boundary conditions. And we do not know, at least we do not know how or at least we do not have so far sufficient information to be able to say something meaningful about these boundary conditions and to be able to pass to the limits in them. Nevertheless, at least, again, we have existence for the semi-discrete problem. Okay, so now concerning the discretization of this problem, if you recall, well, the equation for the voltage was Poisson equation, nothing fancy there. The equation for the charge, it was a convection diffusion equation, and the velocity is pretty small in this phenomena, so nothing exotic. But we had a Canhillier-Navier-Stokes problem with variable density, with non-standard boundary conditions. So let's talk a little bit about this. So let's recall what the equations look like. So we had the phase field equation, the chemical potential, a dynamic boundary condition for the phase field, Navier-Stokes equations with variable density, And now, well, let's say we replace all the terms that involve all the other quantities by some forcing term, and we have the generalized Navier boundary condition. One good thing is that, again, this system is energy consistent. Well, in the energy equation for the electrowetting problem, just take voltage and charge equal to 0, obtain an energy law for this guy. And what we want to do is to build a discretization scheme for this system. In space, there's nothing difficult, Gagliarkin, finite elements, but in time, there's a lot of difficulties, and let me explain which ones are they. Well, first, this boundary condition, the generalized Navier boundary condition, is something very non-standard. It's something actually very controversial as well in the literature, because the reason why this boundary condition was introduced was to solve the so-called contact line paradox. The contact line paradox basically is it is generally accepted that you need to so let me have a pencil. So let's say this is a solid, and we have a two-phase fluid here. Usually, and what is accepted, at least for homogeneous flows, is to write no-slip boundary conditions on any solid wall. But it turns out that this would imply that well, there's no movement between the phases, and so, for instance, the droplet I talked about earlier would, no matter how much you incline the ankle, it's always stick to the surface, and then it's not going to move. Obviously, this is not true, and so this is a paradox, and that only tells you that this boundary condition is wrong, or at least is wrong in the vicinity of the 3-point contact line. And so there's a lot of controversy in which are the correct boundary conditions for contact lines, and there's yes.
So this is actually impenetrable boundary, right?
Yes.
So even if you put the drop top, so what's actually the contradiction?
So okay, let's say we have this inclined plane. We have a droplet here, and we have gravity. Because you're applying no-slip boundary conditions, that means that the velocity of the points here and here are always going to be 0. So the droplet may fall on top, but there's always going to be a very
normal component 0. Right?
No, that's impermeability. No-slip is normal and tangential.
Yeah. Oh.
Yeah. Okay. So there's a lot of people that say that there's some types of boundary conditions that should be imposed there. There's very different schools of thought in this, and they don't like each other. So I'm just saying, if we accept that this generalized Navier boundary condition is the way to go, let's see what happens. Regarding computations, there's a lot of people that deal with this type of phenomena. If you go, I don't know, to computers of fluids or JCP, there's a lot of papers that compute this kind of things. Basically, what they do is just that they add an extra force or an extra term that comes, in my understanding, out of nowhere. Is just to get the pictures the way they want them to. As far as I know, there are only 2 papers where this generalized Navier boundary condition is addressed. The first one is by Gervon Leliev, where they use basically an ALE approach. The second one is by Manservisi and Scarbovelli, where they again do some type of interface tracking using volume of fluid. What we want to do is to do something more general, do it for the Canhiller or diffuse interface case. But before we do that, we need to discretize all the equations, then we deal with the boundary conditions. So the Canhiller equations is a 4th-order system, so something not so standard, at least to me, to deal with finite elements. So we do what is called operator splitting, but that is basically we just keep the phase field and the chemical potential in the equation in this mixed formulation, if you want. And there's been a lot of work in how to do this and showing that this is stable and that is the correct way to go. For the Navier-Stokes equations, the usual way or the most advocated one, as far as I know, in the literature, is to use fractional time stepping. So it's basically a generalization of the projection method of Temam and Chorin. And Jean-Luc Hermont and one of his students extended this approach to the variable density case. And this is what we're going to use. So these are the building blocks that our scheme is going to have. So here's the scheme. First, we look at the Cahn-Hilliard part. And well, as I said, we just solved for the Cahn-Hilliard problem. Although having the splitting, meaning we keep the chemical potential in the formulation. Then we do fractional time stepping, which basically means we decouple the incompressibility from the diffusion, the Navier-Stokes equations, which is what this expression is trying to tell us. Well, notice that this P sharp is explicit in time. And then to find the new pressure, we just do penalization. So we know that the divergence should be 0, and that the pressure is the Lagrange multiplier that enforces the divergence of velocity P in 0. So we penalize the fact that what we computed in the previous step is not solenoidal by solving this problem. And we can show that if the stabilization constants that we introduced before are large enough and large enough in this sense, then the scheme is going to be stable independently of the choice of time discretization parameter. Of course, originally, the peaceful Landau potential is something that is fourth order in this argument. So we could never satisfy this condition. However, we can say, for instance, modify it, restrict it to quadratic growth, a little bit away from the points where we want to have the minima. And then, well, if it is quadratic, this is a constant, and this is easily satisfied. This is good not just for, say, stabilizing the problem, but also there's some work by Caffarelli and Müller that tells you that in the Cahn-Hilliard equation, if your potential is quadratic, then you can have uniform L-infinity bounds. So in some sense, that's reassuring, telling us that this modification is, at least for analysis, a better way to go. The interface energy is given just by an interpolation between the surface tension of the two materials with the solid. So it's a smooth and bounded function. So again, this is very easy to satisfy. One last comment is that here we're taking this expression implicit. At this point, we do not know the new velocity, but we're using them for the computation. So again, this is not completely implementable because these two steps are coupled through this. However, in practice, if you treat them semi-implicitly and under, say, CFL-like condition, you can show that this scheme is stable under the same assumptions as well. So at least we have a scheme for the weird part of the problem that we know is not going to blow up. We know that each one of the pieces converges. Hopefully everything together will too. And let me show you a couple of numerical illustrations. First, about this technique for the Cahn-Hilliard-Navier-Stokes problem. This is droplet relaxation. So let's say we have a droplet of a heavy material. This is the red thing. And under the action of gravity and the fact that the contact angle here is not the one that the droplet would have at equilibrium, it's going to start moving. And actually, the gravity is just to accelerate the process. If we didn't have gravity, the same would happen, just a little slower. So the thick line is the current position of the interface of the droplet. The dotted line is the original, and the arrows are the velocity. So we see first that this contradiction is not happening. The interface is moving, and if we wait long enough, it's going to reach the equilibrium contact angle that we had, which was pi/4. If we wait. Okay, you get it. It moves. The next one is the next example that I want to show is about electrowetting. So, as I said, the only weird part of the electrowetting system concerning discretization was the Canhillier Navier-Stokes. So what we do is we take the information that we know and we take everything that we do not know explicitly. So basically, we solve the elliptic equation associated with the voltage, taking everything else that is in the problem explicitly. Then we solve the equation for the charge, taking everything that we do not know, namely the velocity and the phase field explicitly, and the voltage that we just computed. And then solve Canhillier Navier-Stokes using the technique that we just described. Of course, we know that each one of these components works, converges, but there's no guarantee that this would imply that all this process together has to converge, has to even be stable. So something worth investigating would be stability or convergence of this scheme, or that maybe there are smarter ways of doing this. I don't know. Nevertheless, this is very simple, but yet very similar to the illustration that I had in the very beginning of the talk. Let's say these green lines, these grid stripes, are the plates. This is a fluid, and this is a heavier fluid. And at the beginning of our simulations, we apply a voltage just from 0, so on this part. And if we're doing everything correctly, the same, something similar to what I showed in the beginning, to the picture that I showed in the beginning, should happen. So obviously I'm just zooming too close to the bubble so that it is interesting. And as you see, and as I was trying to explain in the beginning, because of the voltage that is applied to just part of the bubble, the surface tension between these two fluids is being changed. That generates a force that makes the droplet move. If displaced. You activate the voltage, and that creates the. Obviously, these lines are the ISO lines of the voltage. Okay. This is all I had to say today. Let me just rewind and remind you of what we talked about today. So we talked about diffuse interface model for electrowetting. We derived the equations that govern this phenomenon from physics. We showed that the fully discrete problem always has a solution, and that the semi-discrete problem not always has a solution, but under this restriction on the permittivity of the medium. And I also show you an unconditionally stable discretization scheme with for the Canhillier Navier-Stokes equations that can be used to address the problem of moving contact lines. Something that we will be thinking about in the future is how to better discretize this problem, and of course how to pass to the limits in the time discretization parameter. And although this simulation was very nice, as I said, one of the main advantages of phase field methods is that they can handle very easily topological changes. So we want to simulate, I don't know, 2 droplets merging, 1 droplet splitting, and our model is 3-dimensional, so we should do some 3D simulations. Okay. Thank you.
So we have time for some questions.
Yes. So I just want to make a comment. So right here you have a coupling of Computational and Navier specifications. But a couple of years ago, Xiaobin Peng at the University of Tennessee published a paper on science channel neural analysis, solving this kind of coupled problem. Mixed formulation. Do you think that can try?
And here Navier slopes like something funny. I think the problem that he addressed was when the density was constant.
Okay. So right here is more complicated.
Yes, we have a variable density which complicates things a little bit more.
I know some other people like Jiaxing that do use the spectral method.
Yes. Yeah, I'm very aware of the work that Jishan did. Actually, this discretization scheme is very similar to one that he published in Science of Scientific Computing last year, 2010. The difference with that is that his method is to solve these type of problems with this boundary condition. So we have something extra.